Good morning, everyone. In today's lecture, we will continue what we have started in last lecture. Today, we will be looking at the force between two current carrying wires. So those two wires we have here, they have currents going through them. And as we have seen earlier, when we talked about the force due to a charge that does exist in an external magnetic field, and we said the force exerted on this charge is indeed the cross product of the velocity times the magnetic field times the charge. Now here we have current going into a wire. It's not one single charge. Those are charges that are flowing per unit time. So in this case, if we want to define, for example, the force exerted on wire number 2 here, which is I2, and those two wires, as you can see, they're going in the same direction. So due to the magnetic field induced by the wire that has the current I1, so the current I1 in this wire is inducing a magnetic field, and this magnetic field is the one that is exerting the force on the second wire. So here I will be calling F as F1 on 2, and now it's not one single charge, it is a current. This is current, this is the current I2 L, which is basically here, this L is the length that I would like to evaluate the force on. So in this case, cross B1, which is the one that is inducing the magnetic field. So if I want to calculate now this force due to the wire 1 on wire 2, then it will be I2. This is the wire that the force is exerted on, L cross the magnetic field due to the wire number 1 that is exerting the force on my second current here, I2. So in this case, I can say F1 on 2 equals to, now if the direction of the L is going, let's assume that the direction of the I2 is going along the y-axis, and then x is this way and z as in this way. So in this case, if I2, which is basically here defined by the vector L, equals to L j hat cross B1, as you can see, B1 here due to I1 is pointing in the positive x direction. So this one is B1 I hat. So in this case, F1 on 2 equals to j hat cross I hat is minus k hat, and the angle is 90 degrees. So sine theta is 1. So I ended up here with I2 L B1 minus k hat. So F1 on 2 magnitude is I2 B1 L. Now I can define the force per unit length, which is, as you can see here, so F1 on 2 equals to I2 B1. This is so if you want to calculate the total, then you have to multiply by the length of the wire for the I2, the one that I2 goes through. Now I can also say that F1 on 2 over L in terms of the current. So this is I2 times B1. B1 is a mu naught I1 I2 divided by 2 pi 2 pi r. So we can see here that the direction of the force is in the negative z direction, assuming going up is z, then here going down, as we have derived earlier, is minus k hat. So in this case, this wire would be attracted toward the wire number 1 that has the current I1. Now, if you evaluate the force on I1 due to the magnetic field coming from I2, you'll see that the force would be also pointing upward, which means that both wires will be attracted toward each other. So the conclusion we can get is the following. If I have the current traveling in the same direction, which is, as you will see in the next video, they call it parallel, then I have an attractive force and the two wires will be attracted toward each other. If I have the currents going in the opposite direction, which basically called as a series in the video in the next slide, then the force would be repulsive and the currents will go in the opposite direction. So here, this is the repulsive case that is called series in this video because they connect those two wires in series, and that's why the current is going to go in this direction and come back in this direction. So this is the series case, and in this case the currents are in the opposite direction. Here I have a repulsive force. If I have the currents going in the same direction for both, which is the parallel case, then I have an attractive force. And always remember that this force is due to the contribution of both currents. Both currents are contributing into that force. Now we will introduce Ampere's law. As we have seen earlier, Gauss's law was very useful in calculating the electric field due to the symmetrical continuous charge distribution in some structures. We managed to use Gauss's law to calculate the electric field using Gaussian surfaces that are symmetrical shapes. Now, the same thing we can apply for the in the case of the magnetic field. We use what's called Ampere's law. Ampere's law states the following: the line integral of the magnetic field along a closed path equals to the current enclosed in this path times the permeability of the medium that I have this magnetic field induced in. So in this case, if we are to look at this example, again, the closed line integral of the magnetic field over this closed path is given by the closed line integral B dot dl. As long as this path is enclosing wires that have currents, then I do have a value for this integral. If this path does not enclose any current into it, then the result for this integral would be 0. So how do we look at it? We look at the path regardless of this path. If this path is a closed path and this path encloses currents, then this integral has a value. If there are no currents, or if the net currents inside this closed path is zero, then this integral would be zero. So it's not only the existence of the current. So for example, if I have another current that is going in the opposite direction and the same magnitude, I, then the net current enclosed within the surface would be zero. Now let's look at this example. Here we have to rank the magnitude of this integral, the closed uh, path for the magnetic field along that path. For those paths A through D, we need to rank them from the greatest to the smallest. So let's look at here we're looking at the magnitude again. So let's look at surface A, for example. In surface A, we have this surface enclosing all the currents. So let's look at the net current, the magnitude of the net current. So I have here 5 out of the page, 1 out of the page. The summation to this is 6. I have 2 into the page. So the A is giving me 4 ampere magnitude. B, B is this path where I have 2 into the page and 1 out of the page. The net is -1, magnitude is 1 ampere. C, C is this path where I have 1 ampere out of the page, 5 out of the page. The net is 6 ampere. That's the magnitude. A, B, C, D. Path D is enclosing 5 out of the page, 2 into the page. Net is 3 ampere. So now ranking them, C would be the greatest. Then comes A, then comes D, then comes C. So the answer is CA, D, B, which is D. Now we will be applying Ampere's law on a solenoid. So if we have the solenoid that uh, has the magnetic field, uniform magnetic field inside, given by B, and we know the magnetic field outside is very weak in comparison with the magnetic field inside the solenoid. So if we apply Ampere's law, we'll be writing this equation, the closed path integral for the magnetic field over this path that we have drawn here. We have this closed path made of a rectangular shape with a length L, such that it forms a closed path, and it, as you can see, captures uh, those numbers of turns inside this closed path. So if I am to now write Ampere's law for this structure, it will be the magnetic field integral over this closed path, where dl here is the differential vector element, and this equals to mu naught I enclosed. Now, if we look now at those 4 paths, we have this integral for the magnetic field over this dl will be equal to the integral of 4 paths. The first one would be a to b dot dl, plus the second integral is b to c dl plus the third integral is c to d plus the fourth integral is d to a. Now, because the magnetic field is very weak outside going in this direction, we will assume that the integral over the path from C to D from C to D is zero because the magnetic field is zero, assuming the magnetic field is zero. For the other two paths, the one from B to C and D to A, we have the differential element being perpendicular on the magnetic field that is here. So in this case, the dot product would be also zero. So this one is zero and this one is zero as well. In case of the path along the B to C, we have the magnetic field being perpendicular on the differential element. So this is going to be zero. So at the end, I will end up with the integral from A to B for the magnetic field dot dl equals to I enclosed mu naught. Now, if I have my coordinates as y, x, and then this is z, so in this case I can see that the magnetic field B is going in the minus j hat, and I have also the differential element dl as a vector is also pointing in the minus g hat. So my integral from A to B basically is going to be A to B for B minus j hat dot dl also minus j hat equals to I enclosed mu naught. Now I enclosed is indeed I see the current every turn, every cross section here defines a current I. So I have here the I enclosed is basically the number of the turns, one, two, three, four, whatever the number of the turns times I. So this is the I enclosed. The dot product between minus j hat and minus j hat is going to give me B dl A to B equals to mu naught n I. Now the integral over this differential element is going to give me L. So now B can go outside because it's uniform. And now this integral for L from 0 to L for the dl equals to mu naught n I. And then B, this is going to give me L, the length L equals to mu naught n I. Or I can say B equals to mu naught ni divided by L, and then I can introduce a new parameter here, n small letter, that is n capital divided by L, where this n is number of turns per unit length, n small letter is number of turns per unit length. Then I can write now the magnetic field, the magnitude, in terms of this mu naught and I for the solenoid. So this is the magnetic field for the solenoid. Now let's look at this example. In this example, we have uh, one, two, three, four closed paths. We need to rank them in terms of the magnitude for those paths from greatest to smallest. Again, if we look at those paths, all those closed paths, they encloses the same current except for path B, as you can see, does not enclose any current. So B would be 0 and all the rest will be the same. So I have A equals to C equals to D, and all of them are greater than B, where B equals to 0. So the answer to this is B.